this lesson is 1.6, solving systems of equations. And I hope we can see the graph. I'm not sure how much of that you see. I'll try to be rather informative when I talk about how we're graphing. But we're going to solve a system of equations. Okay? And what a system is I'm going to move it over here. What a system is a two or more equations involving the same variable, the same variables, because we're going to have two of them. Okay, so basically, we're talking about two lines and what two lines do. Geometrically, those lines can do three things. Lines, we're going to start with two, so I'll just say it that way. Two lines can do three things. Their relationship can do three things. The first one is they can intersect. Okay, so they intersect in a point, and we're going to show that several different ways. This is, we get an ordered pair as a solution. We get an ordered pair as a solution. Ordered pair solution, and it's only one ordered pair solution. And this system actually has a name. This system is called a consistent independent system. So the directions in some of the problems will say it lists as consistent, independent, consistent, dependent, or inconsistent. Okay, the second thing that two lines can do is they can be parallel. Okay, so this was intersecting. I should have wrote that. Intersecting lines. Okay, they can be parallel. Okay, the parallel has no solutions. They go on forever, and remember in geometry, we wrote parallel like that. And in parallel, this system is called inconsistent. Okay, inconsistent, and it's not independent or dependent. It's just inconsistent. Okay, so I'm going to put a line here so you can separate those. The third way that we can do it is if a line ends up on top of a line, and these are called coinciding lines. Let me spell that for you if you can't read it. C-O-I-N-C-I-D-I-N-G, coinciding lines. Coinciding has infinite solutions, so there's the solutions of all these points are solutions. And this is also consistent because it intersects. So it gets its name consistent by the intersection, but then it's dependent, not independent. Okay, so these are the three things that two lines can do. All right, they can intersect, they can be parallel, they're coinciding. All right, we have some methods to do these to actually find out whether they're intersecting, coinciding, or parallel. The methods, the first one is the graphing method. Okay, the second one is substitution. And the third one is elimination. So graphing, substitution, elimination. I do most of the time like graphing because graphing allows us to see what's going on. Substitution and elimination do not do that. Each one of them has their benefits. Elimination is probably, it's E-L-I-M-I-N-A-T-I, pull in. I don't know if you can see the I there. But elimination is probably the quickest and most accurate. However, you can't see your solution. Substitution works in special cases, but it's very difficult in many cases. Graphing, same thing. You know, if you got two lines that are easily graphed, it's awesome. If not, it can be a pain. So the first method we're going to show is the graphing method. Okay, we're going to show the graphing method, and we hope that the lines end up intersecting on a point that is shown in the graph. If not, it's very difficult. So I'm going to take one in which that happens. 2x minus y equals a negative 1, and 2y plus 5x equals a negative 16. Okay? Now, you will notice that in elimination and substitution, that oftentimes in elimination and substitution, we write the equations on top of each other. But in this one, we write them off to the side because we're going to solve for y. So I have, on this one, I'm going to move the 2x over, so I have plus a negative, so I have a negative y equals a negative 2x plus a negative 1, and then I divide by a negative 1, and that gives us y equals 2x plus 1. I hope I did that right. Okay, this one I move the 5x over, and I'm going to put it in front because we want it in slope-intercept form. So that's y equals mx plus b. So now I divide by 2. This one's a little bit more complicated. Y equals 5 halves x plus a negative 8. You'll notice that I separated the slope from the x so it's easy to graph. Okay, so what I'm going to do is I'm going to graph these two lines. I hope they intersect in a point. So the first one, remember, this is the y-intercept. And so I'm going to go up 1. And then my slope is 2, so I go up 2 over 1. And I keep doing that so that I have more than 2 points. It's much easier to graph when you do that. And then I draw a line. Once again, I'm hoping that my lines intersect in a point that's shown on the coordinate plane. The next one, I have a slope of a negative 8, right? So I go clear down here. 1, 2, 3, 4, 5, 6, 7, 8. And it's clear down here. And then I have a slope of 5 halves. So I go 1, 2, 3, 4, 5, 1, 2. 1, 2, 3, 4, 5, 1, 2. Now 1, 2, 3, 4, 5, 1, 2. I'm not seeing there's intersecting. So let's see where I made my mistake. Did I copy the problem down right? Right here, I didn't, when I moved it over, it wasn't an 8. So you can see how easy it is to make that mistake. All right, so I still have a y-intercept of a negative 8, but now my slope is a negative 5 halves. If I go down here, it's kind of confusing. But what I can do is I can move the negative to the 2. And so what happens is I can go up 5, 1, 2, 3, 4, 5, and then go over 2, and look, it hits there. And that's where they intersect. So I don't have to create any points. That was pretty lucky after my blunder there that I got that. So here we have the two lines intersecting in this point. Now the solution then is 1, 2, a negative 2, down 3. Okay? So down 2, or left 2, excuse me, and down 3. So that is my solution. So this one is a consistent, independent system. And I can write that if they ask me to do that. In some of the directions they do. All right, the next one we're going to do is substitution. And once again, substitution is wonderful on some of them, not so much on others. I'm going to pick one in which substitution is pretty easy to do. 5x minus 3y equals 23. I'm going to do 2x plus y equals 7. I'm going to make sure I copied it down right. Let's hope I don't have any blunders on this one. Okay? So what I do is I try to solve for one of the variables in one of the equations. Now the easiest one to solve for is this one. In fact, if you solve for x here, you would have to divide by 5. If you solve for y here, you'd have to divide by negative 3 and so on. But we have a 1 here, so those are really nice to work with. And so substitution, when you have a coefficient of 1, that's the ones that you want to go after. So what I'm going to do is I'm going to move the 2x over. I'm going to make sure that it's like this one. When I move it over, I make sure that it's negative. It's very easy to forget to change that sign. Now I have 1y here. If I had a number here, I'd have to divide by it. Luckily, I only have 1. So now what I'm going to do is I'm going to circle this, and I'm going to put it in for the y on the first equation. So I put it in right here, okay? and I just substitute in. So I have 5x minus 3 times negative 2x plus 7 and equals 23. So you'll notice that I no longer have any y's, and that was my goal. Okay, so now I'm going to change this to plus and negative. I'm going to solve for x. 5x plus 6x, distribute it through, plus a negative 21 equals 23. I can add these together, and then I just solve by subtracting a negative 21 from both sides. And then I have 11x equals plus positive 44. And that's going to work out nice because I know that it's divisible by 11. So x equals 4. So I already know that this line, these two lines intersect, and the x value is at 4. Okay? Now, since I've circled this, it's very easy to go back and substitute in. That's why it's called substitution. Y equals a negative 2 times 4 plus 7. Actually, that's kind of misleading. The substitution part comes from this going into that. That's where it gets its name. So I have a negative 8 plus 7, so I have a negative 1. So my ordered pair is 4 and negative 1. Now, if you should happen to solve for y first, make sure that you write it in the correct order. And I have a lot of students that miss it on the test because they put this one first because they solve for it first. But if this is y, it still needs to go in the y part. So this is a consistent independent line that intersects at 4 and negative 1. What would happen if it was coinciding or parallel? Well, when you solve for this, you would get your x's would cancel, and you get like 4 equals 4. If you have a true statement, 4 equals 4, then this is a coinciding system, and all points are infinite, so you put infinite points. If you would have something where the x's eliminate, and you have 7 equals 4, those two numbers are not equal, and therefore it would be parallel, no solution. Okay, so that gives you an idea what that is. The last one is elimination, and it is, like I said, the quickest, but it also, and it's the most accurate if you have fractions. But elimination also, you cannot see the problem. So we're going to do this one. And, oh, that one's too easy. I just noticed that, the threes. Let me find one that's a little harder. Okay, here we go. 8x minus 3y equals a negative 11, and 5x plus 2y equals a negative 3. Okay. All right. So, well, elimination I always add. I know some people teach to subtract, but I always add. What I do is I change all subtraction to addition, and I try to get opposites. Now you can see that I can get opposites here, I can get opposites here. I choose to get opposites here because they're already, one's negative and one's positive. So I can multiply by positive numbers. So what I do is I find the least common multiple between the two, which is 6. So I'm going to multiply this one by 2 and this one by 3. Okay? And now I'm going to distribute the 2 throughout. So I have 16x plus a negative 6y equals a negative 22. Do not forget to extend the 2 to this, and that happens a lot. Same with the 3, so I have 15x plus 6y equals a negative 6. Notice that I should get opposites where I'm trying to eliminate. So now I'm just going to add. So I have 31x equals a negative, is that true? Negative 6, I'm getting a negative 28. I don't think that's correct because I remember the answer. Let's see if I copied it down right. Another blunder. 8x minus 3 equals a negative 11, 5a. Okay, let's see where I messed up here. Oh, okay. I bet you saw it right away. You're probably yelling at me right now. This is, I added them. 3 times 3 is a negative 9. You can see how much of a problem that is. All right, that made a huge difference. 31, okay? So I divide by 31, and I divide by 31, and I get x equals a negative 1. Okay, once again, I solve for x first, so that's kind of nice. Now this one's a little harder to substitute back in. I can substitute in here, 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 or here. Obviously I'm going to put it in for the x. Not obvious, but I am going to put it for the x. I'm going to choose this one because that's smaller numbers. So I go 5 times a negative 1 plus 2y equals a negative 3. Once again, I've eliminated the x's, so I have negative 5 plus 2y equals a negative 3. I subtract a negative 5 from both sides, and I get 2y equals 2. So y equals 1. So my ordered pair, this is a consistent independent, is a negative 1, 1. This is a consistent independent. Once again, if I'm doing this and the x cancels, and I get 4 equals a negative 1, then I have a no solution. I have parallel lines. Or if I get a negative 1 equals negative 1, I get coinciding lines. Other than the mistakes, I hope you got something out of that. Those are the 3 methods that we're going to use. You'll notice that it's very easy to make those mistakes when you're multiplying across. So please do that better than I did and when you're moving things. So watch those areas. All right?